Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max, Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two. Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No. But how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnets sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on. Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up, oh, look at that. It could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, We need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
And we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, haha, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz. Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan. Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah, this is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Let's get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet me. I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science.
so I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, Experiments at Large, Magnetic Levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, no. Maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, Experiments at Large, and we'll see you again as soon as we get into the camera.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today's episode is about friction.
How can I hang onto this rope without falling?
Can we reduce it so we can slide around? I'm going towards the wall! Can we increase it so I can climb a wall?
I did it!
Can I use it to fly? Yup! Friction! Today on Science Max Experiments at Large.
Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're going to see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Oh, that's got it.
Oh no, this isn't the Science Center. Did I go back in time again? Oh.
it is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in
No,
case?
it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on. Let's go. Russell's made it.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. A little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset. Uh-oh. The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil.
How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
Right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
Air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the top.
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay. Uh-oh, twist it so it doesn't...
He's losing his air.
Okay.
All right. On you get. You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go.
It doesn't...
Still way too much
It doesn't
friction
feel
on
like
No.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon, something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf blower.
Right?
High fiving.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs, when we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, kind of prefer my carbon where it is. Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then, Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower-powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at this.
That's amazing.
It's good, right?
Oh, yeah, I love the
So-
tube. You know, high volume of air through that.
Yeah.
So yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is a leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air.
I can't control it!
Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me.
I'm going towards the wall! It's like human air hockey! Okay, a little bit unstable. Do you want to turn it off? Wow, that worked amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction
Yes.
down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom. Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
That works for me.
And then we could build two of them, and we would have two discs and two ways of moving them.
Are we gonna race?
And we can race! Yeah! Okay,
Yeah.
race. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena,
Hey.
this is amazing.
Thanks, I made it myself.
Wow,
Ready to climb it?
absolutely. Here we go.
Way to go.
Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right, and the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right,
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my drink. we go. Oof.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro,
Wow.
right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready?
All right, here we go. Ha ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have 2 hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got 2 low friction hover discs, and I'm gonna use the low friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high friction rubber ball stick.
Start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Go ahead and defeat him! He's way back! Oh, he's way back for the win! It's the winner!
Jake crosses the line!
Yes!
And here we have our winner! Yes! Over the finish line, it feels way back over there.
Oh, man.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait, I have an idea. Wait, hold, I need your help. Come on. I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Unfortunately, we can't hear what Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work. Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helen and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines. And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh no! I'm out!
Yeah! High five! Yeah! High five! Yeah! Okay, wait. Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? Larger fire extinguishers?
I think so.
Oh,
Okay.
yeah.
See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, we can get like a rack of extinguishers. Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large. Carbon is an atom that is the basic building block of all life as we know it. You, me, I hit myself in the head with the friction sign. That's more of an impact, not friction, really. How can you destroy my life anymore? Set, huh?